Hello everybody, and welcome to my talk, Lessons Learned from a Red Teamer's Journey into the Kernel. So my name is Khang. I'm a Red Team engineer at Palo Alto Networks. I started in the industry doing binary analysis and binary analysis research and vulnerability research in the mobile space. And then I moved over to red teaming, focusing on malware and exploit dev. Because I enjoy seeing my exploit in actions. So for this talk, I will start by going over my motivations on why I want to do this research, why I think it will benefit other red teamers to moving to kernel as well, and then I'll go into examples of threat actors operating in the kernel. In the next two sections, certificate-based attacks and BYOVD, we'll dive into details of how we can simulate these attacks as red teamers. Then in the last two sections, we'll cover what are the defenses for these attacks, their strengths, weaknesses, and then potential gaps in the for future attacks as well. So motivations, right? So as red teamers, we typically operate under certain principles like least resistant path, right? Ideally, you do just enough to achieve the objective, no more, no less. You blend in with legitimate activities. You don't stand out. You take advantage of the, it's a feature, it's not a bug, as much as you can. And then any tools that you deployed have to be reliable because, to avoid any crashes since they might raise suspicions. Historically, kernel attacks can be unreliable, so red teams tend to avoid the kernel altogether because it can cause blue screen of death, which could lead to raising alarms. You lose the foothold. Prime examples of that would be Eternal Blue MS17010. However, in recent years, with EDRs gaining visibility by leveraging combinations of userland hooks with kernel callbacks, both red teams and threat actors found that operating stealthily purely on userland is getting more and more difficult. As a result, we've seen significant increase in threat actors adopting kernel attacks into their arsenals, so as adversary simulators or emulators, however you want to call it. It's our job to figure out how we can adopt and integrate them as well. So threat landscapes, right? So first one is abusing certificates. The first avenue of kernel attacks is abusing certificates. Even though Microsoft has been restricting the process of signing a driver, we still see rootkits being signed by legitimate certificates that have gone through the attestation process. This raised the possibility that there might be driver signing as a service for malware developers out there that possess unlimited number of WHCP certs. Also, you might find leaked certificates from hacks as well, like the NVIDIA dump that happened last year. It has a certificate for code signing there as well. The second most popular avenue for kernel attacks is possibly BYOVD, which is bring your own vulnerable driver, where attackers exploiting known vulnerabilities in signed drivers to gain arbitrary read and arbitrary write. From there, they can temporarily disable some mitigations by either blinding EDRs or just kill EDR altogether. Since the beginning of this year alone, we've already seen several malware campaigns that exploited vulnerabilities in Intel drivers, Process Explorers, as always, Genshin's anti-cheat drivers, ENE technology, and Zemana anti-malware driver. What's also interesting in some of these drivers, is that they've already been known to be abused by threat actors, right? Like the Process Explorer driver and the Zamana anti-malware driver. We've seen that in the wild for a couple of years now. And they've been blocked by blocklist, right? And however, they can still be used by just renaming or sometimes just repackaging. And then we'll go into some of these weaknesses of the blacklisting approach later in this presentation as well. So certificate-based attacks, right? So as red teamers, adversary simulators, how do you emulate this? The first way we can simulate certificate-based approaches is by purchasing certificates. If we assume that there's drivers signing as a service for threat actors out there, then it would be fair for us to go through this path as well. So in order to go through the attestation signing process of Microsoft, you just have to register for the hardware developer program. You can purchase an EV code signing certificate, or your company might have one. I'm not sure. If you work for a software company, there's a chance that there's a testing EV laying around. And you can download and install the WDK, create a cap file using the makecap utility. This cap file contains the driver itself, the driver INF file, the symbol files, and the catalog .cat files. After that, you can sign the cap file with the EV cert using sign tool. Then you can submit the EV signed cap file using the Partner Center hardware dashboard. There's a link in there with detailed instructions for Microsoft. So the process itself is fairly straightforward. But however, you might be facing a couple of downtimes with this approach as well. Like your certificate might end up being blacklisted by either Microsoft or an EDR vendor. These vendors, they share intel, so then eventually your cert will be blacklisted everywhere. Not to mention, the marketing nightmare you might face if somebody decides to blog about the rootkit in the wild signed by your company cert, right? So another way you can obtain certificates is by searching for them in exposed cloud buckets or GitHub repositories. There are several tools or sites that helps you do just that, like Gray Hat Warfare. As you can see from these, some of these screenshots here, by simply searching for files with PFX extensions, there are more than 17,000 results. However, it's hard to find one that's used for code signing. A lot of them are just for HTTPS. Right? And also, it's hard to find one that's signed by a trusted CA as well. A lot of them are just signed internally for testing purposes, I guess. And not only that, I mean, some of them are password protected, although sometimes it's a weak password so you can crack it. So there are lots of hoops to go through, to jump through, if you go down this path, but you might get lucky. Next is BYOVD, right? So most, if not all EDR solutions out there will hook their DLLs into key userland processes like kernel-32 or anti-DLL or processes that they deem suspicious. For example, in this particular diagram, if a malicious process, malware.exe, calls create process, and that in turn will trigger create process internals, then that will call anti-create user process in anti-DLL, which eventually trigger anti-create user process in the NTOS kernel. So on the kernel side, EDR solutions also rely on the drivers. These drivers will register callback routines. In this particular case, the PS set create process notify routine, and the callback routines can notify the drivers, the EDR drivers, whenever a process is created. And the process for creating a remote thread, for loading images, for creating registry. There are also callbacks for that as well, as you can see for PSSet, create thread, notify routine, OB register callbacks, and CM register callbacks, right? So our goal here is to eventually blind EDRs, right? So we'll need to find a way to remove this kernel callback somehow. And in order to do that, we'll need to be able to read and write in kernel memory. And in order to do that, we'll need to take in consideration some of the mitigations on Windows. So the first one we'll take a look at is DSE, driver signature enforcement. DSE ensures that user can only load drivers that have been signed by Microsoft. Some of this flag, this DSE flag, is located in the ci.dll, and that's the g_ci options. The three key values is 0, hex 0 means disable, hex 6 means enable, and hex 8 is test mode. This DSE value is protected by patch guard, and we'll go over patch guard in the next slide. But the goal here is to override g_ci options with 0 to disable DSE, right? And then we'll have to, after we change it to 0, we do our things, we remove kernel callbacks, and we have to flip this value back to its original value of 6, and I'll go over why we have to do that in the next slide when we talk about patch guard. But this value it's a global non-exported variable. What that means is that this flag, it won't be straightforward to locate it during executions. I mean, you can do it quite easily when you're in WinDebug sessions, but during executions, it's a different story. You'll need to do some offset calculations. There are several ways to do offset calculation here, but one that I've been relying on the most is to use the SIP WHQL enforcement enable functions. The steps that you follow to do is that you map CIDLL into process address space with like load library, and then you locate the functions, the SIP HQL enforcement enable function by using the instruction opcode scanning at the start of the functions. Though I have to warn you, this method is build dependent, so you might want to find out what build version that your target is running on before you execute this. And then after that, we can find the relative virtual address of the global variable g_ci options, right? Since this SIPW HQL enforcement enable function can access this global variable. After that, you find the kernel image base of the module CI DLL, and then you update g_ci options using the arbitrary read and write capabilities that you get from exploiting a vulnerable driver. So next one is patch guard, right? So what is patch guard? Patch guard detects in-memory tampering in the kernel. The way it works is that it pulls critical kernel mode assets periodically. So that means that it doesn't just like watch the structure all the time. It checks in once in a while, and then if it detects a compromise, it'll bug check with the code critical structure corruptions. And some of the key structures that it's being protected by patch guard is L-star MSR, some control registers like CR0 and CR4, among other things. So that's why after we flip g_ci options and remove kernel callbacks, do our thing, maybe load a rootkit driver or something like that, and we have to restore the values. With that in mind, and now we have two paths, right? One is that we can spray and pray. We can flip g_ci options and hope that it doesn't patch guard doesn't bug check, and do our things quickly, remove kernel callbacks, restore it, hope everything's fine, or there's another method which has been suggested to me, but I haven't. I haven't had the need to use that second method. Is that we know that PatchGuard is watching several structures at the same time, right? So what we can do is that we can perform some actions that we know that PatchGuard will have to check, and then during that time we can flip G_CI options. That's safer. But so far, luckily, I haven't had the need to do that. The spray and pray seemed to work for me. And yeah, so and also, but by the way, if you do go with spray and pray, I do suggest that you perform persistence first. In case it fails, then next time around you can continue doing it, and you don't end up losing the foothold altogether. So the key of this is that we still need a vulnerability in a signed driver to exploit, right? And they're generally arbitrary read, arbitrary write vulnerabilities, write what where. You can find a lot of them in several projects like the law drivers project, the living off the land drivers. Previously, before the law drivers project existed, you can find a lot of them in game cheating forums like the Unknown Cheat forum. Sometimes game hacking forum has them as well. So, I mean, there are lots of excellent resources out there, blog posts, thread reports, detailing a lot of these vulnerabilities in this list already, as well as static analysis methodology. So each of them deserves a talk and a blog post in and of itself. I won't be able to do them justice by squeezing some of these vulnerabilities into these presentations. However, I can talk about some of the things that are common and are easily reproducible when it comes to identifying some of these vulnerable drivers, right? So these write-what-where vulnerabilities and arbitrary read, arbitrary write, they're commonly found in OEM drivers. Some of them are like hardware monitoring software like SpeedFan, CPU-Z, Dell BIOS util, and overclocking utilities from OEM manufacturers as well. And these are, I mean, it's hard to call them vulnerabilities when they are intended functions, right? So, by exploiting this, we are actually following the red team principle of, exploiting features, not a bug. So you can, a lot of them will have intended functionalities to, read-write MSR with read MSR and write MSR instructions. So some of the things that you can script for is that you can or first thing to look for in probably reverse engineering these drivers to find those vulnerabilities is to look for suspicious imports like MMIO space functions, locked pages functions, since these functions can map physical memories, can write to MSR, control registers, and so on. And also, a lot of these drivers are recycled and reused as well. Back in the threat landscape slide, I did mention that the Process Explorer driver and the Zamana anti-malware driver were being used over and over again just by repackaging and renaming, right? And same thing here. A couple of examples is read-write everything. They are, I don't know, I think they might be located in Taiwan. They're like a third-party driver development vendor or something like that. But a lot of the OEM vendors out there reuse their drivers. And also the WinRing0 driver as well. I mean, you can see it in Razor software. You can see it in Bitcoin, not Bitcoin, but cryptocurrency mining like XMRig. So yeah. So I mean, you can reuse a lot of these vulnerabilities. There are countless examples out there as well. I mean, so at this point, you achieve arbitrary read, arbitrary write in the kernel. You can flip DSE to load your rootkit or remove kernel callbacks, right? So final step, removing kernel callbacks, right? To remove kernel callbacks, you must first locate them. So there are several ways to do it. You can either do it manually, or you can reuse some of the code out there, like some of the code from EDR Sandblast. At this point, you're executing code in the kernel, so you don't have to worry about being detected or anything like that, because I mean, EDRs don't. I mean, they don't detect things in the kernel. So yeah, you can reuse EDR Sandblast. The way that EDR Sandblast do this is that Microsoft allocates specific numbers called altitudes for all the drivers that need to insert callbacks into the kernel. So Microsoft maintains a list of drivers that have reserved specific altitudes under the FS filter antivirus and FS filter activity monitor list. So that's how EDR Sandblast use it. You can reuse their code. Another way is you can do it manually. There are several ways to do it, but like, you know, from a blog post by Matt Han, he detailed the way to do it with the create process API. The first thing is that you search for, to summarize his methodologies, search for pattern of bytes between the addresses of PSS create process notify routine and IO create driver, and then these bytes will mark the start of the undocumented function PSP set create process notify routine, and then in this document undocumented functions we'll see the references to the target array PSP create process notify routine. So going over some defenses. So a couple of some newer mitigations that come by default on Windows 10 and Windows 11 would include VBS and HVCI. VBS is virtualizations-based security. It uses hardware virtualizations and Windows hypervisor to create an isolated virtual environment to host a number of security solutions, right? So the way that VBS protect against this modifying DSE attack mentioned previously is by parsing the G_CI options with an API called protect driver sections. This API will make sure that the code running in ring 0 can't modify its content. And HVCI is hypervisor protected code integrity, or you might see that option in your computer as memory integrity. It hardens Windows by running kernel mode code integrity within that isolated environment that's created by VBS. Another thing is blacklisting, right? Microsoft maintains a block list. It's called driver block list, or recently there's the law driver project that's a lot more comprehensive. And then another thing that a SOC analyst can do is by flagging service creations and modifications activities for the analysis, because you know the easiest way or most common way to load this a driver for BYOVD is to create a service and then load that driver, right? So future work, well, I mean, from what we read online, from Microsoft documentations and video conference talks and stuff like that, it seems like VBS and HVCI will stop this attack class altogether, right? But not really. So HVCI has a hardware requirement. So it requires Intel 11th Gen or AMD Zen 2. You might think that that's old hardware, so who cares, right? But with the supply chain issues during COVID, and then the number of endpoints that an enterprise has to support, like a lot of older hardware are still around, right? And sometimes even if VBS is enabled, HVCI might not. Like in one of the screenshot I put up there, like you can see that VBS is running, but actually the service is running is only credential guard, because in an enterprise you can't be sure that there is no older hardware. And you know, sysadmin typically create one policy that blanket the whole organization, so you don't really segment the endpoints very well. So there's already a couple of like attacks against DSE with VBS enabled, but HVCI disabled. You can check it out on the blog post up there. Another thing is that blacklist only block specific versions of the drivers and a particular certificate, right? So what that means is that if there is a newer version of the driver with the same vulnerability or a variation of it, the block list is not going to care. I encountered several instances of this, like the speedfan driver and the driver 7 driver. For the speedfan driver earlier this year, when I tried to exploit this speedfan driver, I saw that Microsoft Blocklist blocked the certificate, but there's a, I don't know if it's called newer version. If you download speedfan driver from the speedfan website instead of using the one that's included in publish exploit, then the vulnerability is still there, but it's signed by a different certificate. So that means that it's going to completely bypass the block list. Not only Microsoft block list, but also several other EDRs as well. And another instance is the driver 7. The driver 7 driver from ASUS. I think some of the some EDR vendors out there, they make these mistakes because you know they're ingesting data in bulk, right? There are, as I mentioned before, low drivers. They both red teamers, threat actors. I don't know if threat actors actually do it, but both red teamers as well as like you know EDR engineers, they scraped cheating forums for these drivers. And in one of the screenshot up there, you can see a snippet of the ASUS driver. So on unknown cheat forum, there's a mega thread for known vulnerable drivers. And in there, they only highlighted one driver. It's called ATSZ something, I can't see it, SEIL64 driver, right? EDR vendors, they do just that, right? They ingest this hash, they take the certificate, they block it. Everything's good and dandy, but if you actually go into this GitHub repository, you will see that it actually contains two drivers in there. Not only that ATSEIO64 driver, but there's also another driver called driver 7. And if you read the descriptions, you'll see that this is a typical case of like this researcher, he reported the vulnerability in this ATSC IO64 driver, but then he also said that like, you know, the driver 7 contains this exact same patterns of being able to map physical memory and modifying MSR, but he was just too busy to give them the detail of the vulnerability. So they assigned one CV for one driver, but they didn't assign one CV for the other. So that's why for a while, driver 7, you can still exploit it. The vulnerability is actually exactly the same. The way that you exploit it is still the same as well. So so next is what if in a perfect world, right? The low driver project gets so good that EDR vendors block all known drivers that are being abused out there. And what can you do, right? You can so EDR vendors only block you from loading vulnerable driver. It doesn't do anything if the vulnerable driver is already in the system. So you can exploit existing drivers, right? A lot of enterprise use either Dell laptops or HP laptops or ASUS or something like that. And those laptops, they come with third-party drivers, and they reuse vulnerable drivers, as I mentioned previously as well. And also, like, you can exploit gaps in patches. right? I mean, if you do security at an enterprise, and you know that the enterprise is not going to apply the latest patch because they have to test it first, and there are several reasons around it as well. And you can abuse, like some of the drivers, like Microsoft drivers, have been abused by threat actors in the past year. Is like Win32k, CLFS, which is the common log file system driver, and the spooler drivers. Those are all good targets. There are lots of good resources out there for how you can analyze the patch and possibly exploit the vulnerabilities. So with that in mind, that's the end of my presentations. So thank you very much for staying and listening. And I'll be around for questions if you guys have any.